Hello, my name is Sebastian, and I will be talking today about acausal model augmentation with neural networks. So first, let's unpack the title a bit. What is the acausal part? So in acausal modeling, we want to represent the dynamics of the system as collections of components and connections between them, instead of just working directly with a potentially large system of differential algebraic equations. The large system of differential algebraic equations is still there, and it's still being automatically built, but the main point is that we don't start with that. We don't write that by hand. This can be done in Julia with ModelingToolkit, and there's been several talks about ModelingToolkit already. And the important part here is that we can visualize these connections and components in a graphical manner with block diagrams. And this is the ability to visualize our system in this way instead of just looking at the equation can provide a lot of physical insight into understanding how the system works and how it behaves. And just as an example of like how does this look like, here we have a simple thermal system where we have some heat source that heats up a system of a plate and some a pot. So you're making tea, for example. And this is also in contact with the air around it. And now we can either look at this, or we could also represent this graphically. And this is maybe a bit easier to understand, and it's also easier to visualize, and more importantly, easier to debug, because when you would write this, you need to connect the things in the right way and to make sure that you connected everything correctly. But this all simplifies to just two ODEs. So all of that diagram with multiple components is just governed by these two ODEs. And here, when we compile this with MTK, we see that, these first two equations, they essentially, it is just ModelingToolkit telling us that this is the shortcut for the derivative for the time and so on. So we want to expand this to see what actually happens in there. And we can see that this can get a bit complicated because it includes all the interactions in the system. And now, what about the model augmentation part, right? So when doing UDEs, usually we've seen this example of the Lorentz equations everywhere with how would you do UDEs. You have your system of differential equations, and you add a term from the neural network. Or you can do more complicated things if you just don't want to just add it. But the main point is that here we are working directly at the level of differential equations. But we just saw before that we also have in this representation, we have the block diagram, we have the components, we can visualize that. But if we want to do model augmentation, then UDEs, we don't want to lose this ability of still being able to visualize how the system interacts, where the neural network is, and not just something that would be shoved down somewhere in this equation. And what if we can represent the neural network as a first-class citizen in this system? And this is what ModelingToolkit Neural Nets does. So it's a package that allows you to symbolically represent a neural network as a component in your system. And there's two versions of the API. You can either use a block as a system, or you can use callable parameters, but this talk is focusing on the block interface and how you can use it as a system. And the implementation of this is actually quite simple in the package. We just have the parameters of the neural network, and we just call lux to give us what's the output of the neural network given the inputs to the neural network block. So how can we use this? So this neural network block can be viewed as just a black box thing with inputs and outputs. So we just need to connect the right inputs and outputs in our system, and then it will fully integrate with MTK and all the symbolic simplification stuff and everything that MTK does will be performed on with this neural network block being embedded in the system. So we've seen that we have two ways of approaching this model augmentation, either working directly after structural simplification at the system level, and this is what I'm going to call system level UDEs, and there's actually a talk right after this one, which I think will go into that if I understood the title correctly. And component-based UDEs, where the fact that you are working with components is a fundamental part. You want to be able to enforce constraints on how the neural network interacts with the rest of the system via the block interface and via the, treating it as its own system, which has potentially constraints or has a well-defined interface for interacting with the rest of the system at the block diagram level. Okay, so let's see an example of how we would actually use this. So we are going to start with, again, a thermal system, but we had actually a few slides ago a slightly different thermal system, but we might have forgotten what we put in there. So let's start with a simpler version where we recall that we had a heat source and something that was heating up, this pot component, and we are going to use neural networks to recover the rest of the system that we forgot about. So when we are building this, the full model has a lot of equations which map to the block diagram, and now we are simplifying it, and we observe here that we just have one equation. This is a simpler system, and it's not just a simpler system because it has less terms in one of the equations. It's a simpler system because we have less states in here. So we will also need to introduce a new state with our neural network. And we can also compare predictions of the system from the first part of the talk with what we have right now. And we see they have a slight difference in their behavior. So the pot is hitting slightly faster in this simplified approach. And we're going to try to find out how we can explain this via a new component. So we would want to add into the system the neural network in sort of this way. We want to put it between the source and this pot element, and it will be connected then with everything. But we cannot just put a neural network in the system because the system works with physical units. It works with heat ports. It needs temperatures. It needs heat capacities. It needs heat flow rate. So the neural network just knows numbers. So we need a specialized component that will be our interface to the thermal domain, essentially, for this particular problem. And we want to see how would we formulate this specialized component that interacts in a physical way with the neural network. Okay, so let's take a closer look. So we have first the neural network, and we see here that you need to specify the number of inputs, the number of outputs, and then the network itself, of course. And this can be any lux.jl neural network. And ModelingToolkit neural nets also offers some simple utility functions for building such neural networks. And one important thing to note here is that this neural network that is created by our utility function has, at the end, it has the last layer such that the weights are multiplied with a very small number, so that initially, when we add this to the system, it doesn't affect much, so that we don't start, I mean, the neural network weight will be random at the beginning. So we need to make sure that this randomness doesn't affect the system too much, so that we can start the training from a stable state. What else do we have in this specialized component? We have heat ports. This is how we interact with the rest of the system. That's the physical part on how do we interact with the rest of the system. And now, how does this component work? So this is the interesting part. How would one write such a component in the first place? So the important thing is that when we are working at this level, at the block diagram level, we want our neural network to represent physically meaningful relations. So we need to actually make sense from a physics standpoint when we are building this component. And what do we know from physics about this thermal system? Well, we know that we want a conservative component at steady state. And this means that when the derivative, so here, yeah, the first thing that I wanted to mention, yeah, we have a missing state dimension of the system, so we want to integrate a new state that will be, that is created by this neural network component, and this means that we'll need the derivative of this unknown state will be some function of the neural network output, so that the neural network output gets integrated. And when this derivative is 0, we want the heat flow from port A to be plus the 1 at port B to be 0, so that we have some conservative, the component is conservative essentially. And another thing that we want is that the neural network works usually with small numbers. Our temperatures are, we work in Kelvin, so we need to normalize the temperature value such that it's in the range where a neural network can work with it more easily. So this is how we can come up with these equations of how does one go from just the neural network to some physical component that can actually be put in the system. So now let's put everything together, and you see that we get similarly large system here. And if we take a closer look, we can see that, yes, we still have this neural network is somewhere in here, and this is now simplified to just these two equations. So we have a new state as we wanted, and we can now check if this if this simulates correctly in the initial state, so it doesn't blow up initially. This works. So we can continue by training the neural network. Here we are grabbing the neural network parameters, which are it's just a vector parameter, it's a vector of numbers that we just then update the solution here for. This is using an optimization problem with I should update this to the nonlinear least squares thing, as was mentioned in the previous talk. So yeah, and now we can train this in a two-stage manner. First, we will do some iterations with Adam, and we can see here that the loss is decreasing. And then the last stage, the second stage, we can create a new OD, a new optimization problem where we start from where we stopped with Adam and then do LBFGS, and this will get our trained neural network. And now let's build a new OD problem and see how well does this fit. This is a very simple system, so our system is very small. The neural network was also very small, and this is now fitting perfectly. And one thing to note here, so we only have if you look at the plot here with the temperatures on the second row, this is the only data that we have that we are using in the loss function. But we need other things in the system to match with what would be expected. In this case, since we started with some synthetic data, we know everything about the correct answer. When you are doing this on a more realistic case, you would not know that, of course. But what I'm trying to show here is that we need to be able to match the neural network outputs to the correct physics, not just to fit the data, because fitting the data can be done even if the neural network outputs are completely different from anything physical. And from this, just by training the neural network to fit the data, that is not enough to ensure that your physical behavior is correct. This is why we have to construct that specialized neural network component such that we embed the correct physics from the structure, and that allows us to be able to match this. I mean, actually worked on several iterations of that specialized component until I got it to be physically correct. And this is, I mean, I could get it to fit, but yeah, the physics was wrong. So it's not enough to just train the neural network. The physics part is also very important. And we can now also evaluate the results and see that our trained UD is perfectly matching the results that we expect from the original system. And what's next? We train the neural network, it does everything. So what can we do next? We actually, now that we have the neural network output, we might want to look at, okay, can we actually represent this symbolically? And yeah, we can use symbolic regression to get from the neural network inputs. So we have the neural network inputs, we have the neural network outputs, and this is just a mapping between two vectors. And we want to search for what symbolic expression can get from the two inputs that we have to the one output that we have. And we actually find something that's interesting, and we see here in one of the results from symbolic regression, we have a difference between the inputs. And this, our inputs were the temperatures. So this, and our outputs was the heat flow. So this, again, makes sense physically because we are computing the heat flow rate from temperatures, and we also have some constants there that represent, I mean, these are parameters that if we were to fit like, I think capacitance, heat capacity, or we would get that. So we have a linear system here. So when we replace those components, they were linear. So again, everything matches what we would expect. One thing that I wanted to mention is that symbolic regression will give us how many candidates we want. So we have, I mean, there is no unique mapping, no unique solution to this mapping. So again, we need some, I mean, this can help us gain more insight, but it's not like it's going to just give you the right answer and that's it. Like, it's not magic. And we see that if we look at the other results here, they are almost the same thing. Like here we subtract a very small number from one of the temperatures, so this is basically 0. Here we, another example is, yeah, here again we just changed slightly a bit the numbers here, but the fundamental part is still that we have a difference between these two inputs that's scaled by some constants after. So now that I've gotten to this part, you might have seen talks about dyad, and you might be wondering if there's any relation between this and dyad. And the idea is that with dyad we can represent this in a declarative manner with analysis. So this is an analysis definition for how you could do UDEs, and the idea would be that you don't want to just have to manually go through all the steps. We can formalize all of this and package it in this analysis format so that you can easily go from the block diagram. And if you might have noticed, there were some screenshots of block diagrams that's from dyad actually. And I can also, so they are actually from here. So this is where I took the screenshots from. And here the idea would be that you can go from the block diagram representation to an analysis where, again, you work in the block diagram space. And this helps encode the physics better, and then you can create your own blocks that encode the physics of the problem and do the right constraints from the physical standpoint. And then, yeah, this is upcoming, so this will be available soon. And yeah, if you have any questions about the methodology or about Modeling Toolkit neural nets, let me know. The Modeling Toolkit neural nets also has a new documentation as of this morning. And this example is also presented here, and we can see everything also in the new Modeling Toolkit neural net docs. There was actually also a slightly breaking release for Modeling Toolkit neural nets very recently to simplify the interface a bit. Not sure if anyone was using MTK neural nets before. It didn't have great documentation. It was like this is starting to be the documentation. And yeah, so Modeling Toolkit neural net is from SciML. It's open source, so you can use it. And this is where you would go and learn more about how it works, what are the APIs, and how it can be useful for your own problems. Thank you.
Yeah, so I think Chris is supposed to be chairing this session, but I think he has an overlap, so I will fill in for him. Are there any questions for the speaker?
So just to make sure I heard you correctly, so on that example you gave, the cost function was just on the temperature?
Yeah.
And you mentioned you had to play a little bit with the neural net to get it to be physically accurate. What was that playing you did? Was it?
So here the important part is, let me see if I can go back to the slides. The playing around was this, how does this component work? So let's, the equations here, you can write the way that the neural network interacts with the rest of the system in many ways. Like, and you can get a lot of variants to fit, but the thing is that you have to think about like what physical constraints on the system. Like one of the important physical constraints was that at steady state, you want the system to be conservative. So there is some physical intuition that gets into building this, and this then constrains the way that the neural network interacts with the rest of the system.
Yeah, just so two quick questions. The first one is any recommendation on how you choose like the neural network, how many layers and things like that?
Yeah.
And the second question that is a bit non-related is, have you had cases where, for example, you would, like the addition of the neural network would add non-linear systems to your model because you would basically connect?
Yeah, it can happen that this can create a DAE. So that can happen. The question is if you want that to happen or not. In this case, this was a very simple linear system, and I know that I don't want that to happen. But I mean, and actually in version 1 of ModelingToolkit neural nets, which was working with MTK-v9, we actually there was, because of how the equations were ordered in MTK, we would actually always get a DAE because the updates to the neural network was done via an algebraic equations instead of being already embedded in the update. So that was a side effect of how the symbolic system in ModelingToolkit was interacting, and there were cases in which would give you DAEs or not. So yeah, that's one of the things. And the other one on the recommendations for how many layers and so on. So here, I mean, the thing is that how complex is the missing physics that you are trying to discover with this. So here I had a very simple thing. So I have a very small neural network. You might have seen that it has 4 neurons. Like it's extremely small, but to find something that's described by a line, I mean, it's overkill, right? Like we have 37 numbers instead of just 2 numbers. So even that is very large. But this very much depends on the type of phenomena that you're trying to recover with this method.
Hi, thanks for the amazing talk. I had a quick question. You showed the symbolic expressions that were generated from the symbolic regression.
Yeah.
And gave an idea of how to pick the correct or sort of seemingly correct expression from the available candidates. Are there any guidelines on how to process something like that? And you know, if you know some kinds of behaviors of the system, how do you actually identify expressions that would be most likely to fit better?
Well, there are several things that you can try. I mean, besides having a general understanding of the system and seeing if the terms make sense or not, you can also try plugging that back in. So symbolic regression.gl actually has an interface for going from dynamic expressions, which is the symbolic backend that it uses, to symbolics.gl, so that you can then utilize those expressions in the original MTK model and then see how that goes. And you can then see if, like, you can do predictions, like you just use the first half of your data or something like that and then evaluate how do you do on the rest.
Okay, I think that's all the time we have. Let's thank the speaker again, and the next speaker can prepare himself.